one-dimensional systems which look like x dot equal to f of x. So one-dimensional dynamical system with x running from minus infinity to plus infinity. Essentially, it was dynamics along this straight line over here. I want to stick for some time and a little more to one-dimensional system, but change the variable to theta, so that the dynamics is theta dot equal to f of theta, and the difference is that instead of being described on a straight line, this gets described on a circle. So here is the angle theta, and this has the property that theta and theta plus 2 and pi n equal to plus minus 1, plus minus 2, etc. are the same. So this is what is interesting about theta dot equal to f of theta. It allows for periodic behavior which was not allowed over here. So x dot equal to f of x going along a straight line had to, could never turn back. So you start from somewhere over here, and suppose this dynamics goes on, starts out to the right, you go and end at a fixed point, or get, if you are close to a repelling fixed point, stable fixed point, you can't start, you sort of get kicked off to the left. But you don't have a periodic orbit in x dot equal to f of x, but with theta dot equal to f theta, because of the fact that theta goes round, and once it has gone through a circle, you are back to the same point, there is the possibility of having a periodic orbit in a first order dynamical system. That's why this is slightly different from what we had been doing before, and therefore worth some attention. Now, when is it really interesting? If f of theta is like, let's say, lambda theta, lambda is a constant, which is the thing which we started out with in x dot equal to f of x, then theta dot is equal to lambda theta implies that theta is equal to theta 0 e to the power lambda t, and if lambda is greater than 0, then theta just keeps on increasing. This is certainly not, I mean, here theta keeps on increasing, and this question of this does not arise, that theta and theta plus 2 and pi are going to be the same. That no longer makes any sense. So this polynomial kind of f of theta is not what would be of interest for us. You want f of theta to be periodic, that is f theta is equal to f theta plus 2 pi. So you want to deal with, if I'm going to see some interesting dynamics with theta dot equal to f of theta, the interesting part coming, because if I go by, if I change by 2 pi, nothing should happen, then the kind of function f of theta that you should be dealing with is those which are periodic, which is f of theta equal to f of theta plus 2 pi. So the function f comes back to where it was after we have gone through an angle 2 pi, restricting theta to the domain essentially 0 to 2 pi. Alright, then what What's the simplest f of theta that I can think of? Obviously a constant. So theta dot equal to omega. So f theta trivially periodic f constant. So f theta dot equal to omega, f of theta is constant, so f theta is theta plus 2 pi automatically satisfied. So very good. So theta is equal to omega t plus theta naught, and sure enough, if t is equal to 2n pi over omega, then so t equal to 0, theta is equal to theta 0, and now t equal to 2n pi over omega, so this is equal to 2n pi plus theta 0, which is like theta 0. So after 2n pi over omega, you are where n is an integer, you are back to where you were, and therefore this is motion with periodicity 2 pi over omega. So period of motion, so theta dot equal to omega describes periodic motion with period 2 pi over omega. So that's how theta changes. Well, nothing much over here, but if I have two variables, then it's a little more interesting. So I have point A over here, and let's say I have a point B over here, and the dynamics of A is theta A dot is equal to omega 1, and theta B dot is equal to omega 2. So both of them periodic, theta 1, and now if I look at the difference, so you want to look at, so this is your angle theta A, and effectively this here is the angle theta B, and this difference, what's of interest, is the difference theta B dot minus theta A dot is equal to omega 2 minus omega 1, and if I call this difference phi dot equal to omega 2 minus omega 1, then phi integrates out to omega 2 minus omega 1 t plus phi naught. So if your initial difference is phi 0, so initial difference over here, if that's my phi 0, that's my phi 0 over here, then phi 0 grows with time, so phi of t grows with time until you reach t equal to 2 pi over omega 1 minus omega 2. So at 2 pi over omega 1 minus omega 2, phi is back to phi naught. So this initial difference changes and comes back to phi naught after a rather long period of 2 pi over omega 1 minus omega 2. If omega 1 and omega 2 are reasonably close, then you see these things going sort of more and more out of phase and then come back after a long time. And what this is essentially the phenomena of beats. So this is your beat frequency which is omega 1 minus omega 2. So two of these make a little more interesting dynamics. Alright, so we'll come back to the at the very end of this set of problems to another one with two variables, but a little more complicated. So to get to that, let me try out the theta f of theta, which is a little more ambitious. So f of theta is omega, which was a constant, but now let me add a periodic part to it, which is omega plus a cos theta.
Sir, will not be the mod sign 2 pi by mod omega 1 minus
Yeah.
because if
It's,
it will take sense.
yeah, sure. Yeah, absolutely. So I make the f of theta a little more complicated. Little more complicated is to add to this trivial constant omega part which is a cos theta, which can increase or decrease the frequency with the changing angle. So I now have theta dot equal to omega plus a cos theta, and if I look at this circle over here, then at theta equal to 0, let's say omega a is greater than 0. So a is greater, so theta equal to 0, its theta dot is omega plus a. So over here it is fastest, so that's the fastest that theta can change, so omega plus a, and over here it is omega minus a. So here is theta, so this is slow over here, so goes round, but not with a uniform speed omega, but with a speed which is fast at this point, the fastest over here, then slows down. It is most slow over here, and then speeds up once again, assuming of course that a remains smaller than omega, so no possibility of change of sign. That is, when it's omega minus a, it's still positive and going in this direction. Very good. So what should I be looking at? Number one, I look at these three different cases: omega greater than a, 2, omega very nearly equal to a, and 3, omega less than a. So these are the three cases that you would like to look at. And so it's, if it is omega greater than a, as we said, it simply goes round, right? I mean, the theta changes and comes back. If you started it out from over here, it would go round and come back over there. So it's still periodic motion. But the period is something which I would have to calculate. So you omega greater than a, so 1 which is omega greater than a, it's still going to be periodic motion. But its period t is going to be integral 0 to 2 pi. So your dt is equal to d theta over omega plus a cos theta. So t is going to be, you have to complete one circle, so you go from 0 to 2 pi in theta, and that is d theta over omega plus a cos theta, and that integral is 2 pi divided by square root of omega squared minus a squared. So it's a periodic motion, but the period, so as a goes to 0, you are back to 2 pi over omega as we had over here. And as a becomes bigger, your time period gets larger and larger. And as a approaches omega, which is our case 2, when a and omega are very close to each other, the time period is going to become tremendously big. So time period becomes tremendously big if I am close to, omega is close to a. So let's say omega is a plus epsilon, epsilon greater than 0. And if I look at that time period, it is going to be 2 pi divided by square root omega minus a, which is epsilon, into omega plus a, which is 2a plus epsilon to the power half. And if epsilon is very small, much smaller than a, then I can, to the lowest order, drop the epsilon over here, and the answer is 2 pi over 2a epsilon to the power half. So the time period diverges as epsilon goes to 0 and diverges with the square root, with a power law behavior, which is 1 over square root of epsilon. As you can see over here, that if omega is going to become equal to a, then this integral over here is going to be d theta over 1 plus cos theta, and 1 over omega. So this is omega equal to a. It's d theta over 1 plus cos theta integrated from 0 to 2 pi, and this has a singularity at theta equal to cos theta, theta equal to pi, so cos theta equal to minus 1, the integrand blows up, and blows up in a manner which is not integrable. I mean, integrands can blow up and you may not have a problem. D theta over theta to the power half, this integrand 1 over theta to the power half blows up at theta equal to 0, does not bother you. But this is 1 plus cos theta, the blow up is around theta equal to pi. So if you write theta equal to pi plus phi, let's say, then to look at the region near pi, then this is like d phi over 1 minus cos phi, which is d phi over 2 sine square phi by 2, which means for small phi, this is like d phi over phi square. So d phi over phi square, and that blows up. So d phi over phi to theta, d phi over phi square, and therefore has a problem. So this is what it's you are looking at, that as epsilon goes to 0, then your time period blows up. It blows up as 1 over epsilon to the power half. Now, as that calculation shows, that if I were to do this calculation near for omega equal to a, and extract this answer over here, then I really don't need to do this integral. This integral, not difficult. Either you use a contour or you use the substitution tan half theta equal to x, and thereafter you can get it, and from there. But if I'm looking at omega equal to a plus epsilon, and epsilon is small, and I want the leading order behavior, I don't need to do all that. So that's let's have a look at this. That to concentrate on the integral with t equal to 0 to 2 pi d theta a plus epsilon plus a cos theta, which is equal to 0 to 2 pi d theta over epsilon plus 2a cos square theta by 2. So 2a cos square theta by 2, and my problem is when cos theta by 2 becomes 0, which is when theta becomes equal to pi. That's when I'm hitting this 1 over epsilon and the integrand is becoming very big. So having noticed as before, I mean when I looked at that divergent integral over there, that it's the region near pi which is of vital importance. So you look at theta equal to pi, you set a change of variable theta equal to pi plus phi, then t is equal to minus pi to plus pi. So phi equal to theta equal to 0, phi is minus pi, theta equal to 2 pi, phi is pi, and it is d phi divided by epsilon plus 2a. So it is theta, it becomes pi by 2 plus phi by 2. So it's sine phi by 2, and so it is sine square phi by 2. So epsilon plus 2a sine square phi by 2 till now, it's just a transformation of variable. Now I want to make the statement that look, most of this integral is going to come from the region where phi is small. See, if phi becomes big, then this epsilon, mind you, is much smaller than 1. So if 2a and a is of the order of unity, and then if phi becomes large and sine becomes of the order of unity, like half or 1/3 or what have you, then I have something which is over here much bigger than this epsilon. So the epsilon is going to be effective. Epsilon, let's say, is like 0.01. So I'm talking about an epsilon which looks like 0.01, and epsilon to be effective, this term over here has to be the same order as this epsilon. If this term becomes much bigger than epsilon, you are not going to see the effect of epsilon at all. So the phi that we are interested in has to lie near phi equal to 0, and therefore I can make the approximation that I'll substitute sine square phi by 2 by sine phi by 2 by phi by 2, and therefore this integral is approximately minus pi to pi d phi divided by epsilon plus a over 2 phi square. So this is the key step in all this, that this one over here, this epsilon plus 2a, you look at this and you want to get the approximate answer for epsilon very small. To get the region where the integral integrand is becoming very big, because I have a small epsilon, this term has to be small and of the order of epsilon. If this becomes 100 epsilon, then this is of no use. So you want to restrict phi to very small values, and you want to approximate the integral in this fashion over here, right? I mean, so all right, now this is what I have. Now what? Now substitution, phi equals square root of 2 over a square root of epsilon times x. So you write phi as square root of 2 over a, so your phi square has become 2 over a times epsilon times x squared, and this integral for t, this is now very nearly minus pi. So when this is your limits on x, so is going to be minus pi into square root of a by 2 into 1 over root epsilon, and pi into square root of a by 2 into 1 over root epsilon, and this is dx over 1 plus x squared, and the a by 2 has cancelled, epsilon has come out, and from phi to x I have a root 2 over a, and I have a square root of epsilon, but there is a epsilon in the bottom, so it's this. So it is that into dx over 1 plus x squared. Now what about the limits? The limits, this is 1 over root epsilon here, and 1 over root, so this is like minus infinity, and this is like plus infinity, so this is right, minus infinity to plus infinity dx over 1 plus x squared into square root of 2 over a epsilon. This integral is pi, 0 to infinity dx over 1 pi by 2, so double it, pi, so the answer is root 2 into pi over root a epsilon. So that's exactly what I had over here. So this is, cancel the root 2, so this is root 2 pi divided by a epsilon to the power half, and here it is that I can get this leading order answer just by looking at the behavior of this integrand over here without having to know that this integral, when the exact evaluation gives me this, and then take the limit and come there. You don't need to depend upon the existence or your doability of the exact integral. You need to, if you want to get the asymptotic answer, you just look at the behavior of the integrand and get an answer. So this is, now physically you see what's happening is that when it's fast over here, your omega is, so this fast now, this speed is like 2 over omega. And this slow is very nearly 0, which means that you speed up all the way close to this point theta equal to pi. So you come close to this point theta equal to pi, and then it is taking, there is an infinitely large time to cross from one end of this to the other. So going across this point theta equal to pi is taking you an enormous amount of time. The time that it is taking you over here is exactly the time that we have calculated over here. The true time period is this time plus the time that it takes to go from here to here, but that's a fast time. So the slow part is just at this theta equal to pi, and that is where it is taking this enormous amount of time. So it seems that is why this thing has what is described as a bottleneck effect, that there is a bottleneck over here, so there is a tremendous slowing down, and that slowing down makes the time period go up. So this is the characteristic feature of this f of theta when you are in a situation where omega and a are virtually equal. Alright, so that's case 2. Now case 3 is so case 3 is when omega is less than A, and then theta dot equal to omega plus A cos theta. Omega now is less than A, and what do you think should happen to this dynamics? Huh?
A fixed point.
Yeah.
It has a fixed point, so it will spend infinite time around that fixed point.
So it will have a fixed point. See, now it is, if I want to look at this f of theta, does f of theta have a 0? So f of theta equal to 0, which is this fixed point condition, theta dot equal to 0 for cos theta equal to minus omega over A. Previously, when omega was greater than A, this fixed point didn't exist. At omega equal to A, it just came at pi, and now it's your omega less than A, so it exists. How many fixed points? Two fixed points, right? So there is a fixed point theta star at cos inverse minus omega over A, and another at theta star equal to 2 pi minus cos inverse of minus omega over A. So those are the two fixed points that you have. Which one is stable?
Second one. I mean 2 pi minus.
For stability, I have to do df d theta at theta star, that's equal to minus A sine theta
The first.
at theta star. A is positive. Theta star has to be either in the second quadrant. Yeah, so second quadrant, the sign is positive, so A is real, so this is that one. This is stable. And this is unstable. Very good. So stable and unstable for omega less than A. So as you go to omega equal to A, so you have these stable and unstable. So this is for omega less than A, and now you take your omega coming close to A, and these two fixed points are going to go and merge at this point over here, right? At omega equal to A, they merge at pi and then disappear. Right? So this is the tangent bifurcation in theta space happening over here. And if I look at it near theta equal to pi, I should be getting the normal form of the tangent bifurcation, which you would you can easily see that this omega, you have to expand near, as I said, pi, which is what we had done before. We are looking at this denominator over here. That's the what you have, omega close to A and theta close to pi. So f of theta has the form which you see over here, which is the form for the normal form for the tangent bifurcation. Right? The bifurcation point is theta equal to pi, omega equal to A. So if I'm close to both omega equal to A and theta equal to pi, and I expand theta equal to pi plus phi. Phi is small, and omega is equal to a plus epsilon. Epsilon is small, then f theta will have the form your epsilon plus 2a into phi squared. So f theta is equal to, so in phi dot, so phi dot is equal to epsilon plus a phi squared over 2, so normal form. 10 unit bifurcation. Correct? Right? So works through in every way. Alright, so we have what is happening is that what I am telling you, that if theta dot is equal to f of theta, and f of theta has the form omega plus a cos theta, then there are some interesting results or some predictions that you can get for this dynamics over here. So now comes the question that is there any system which has a dynamics which is theta dot equal to omega plus a cos theta? Is there a real system which has this dynamic? So up to now it was all just maths. I mean, you do the maths and you get, you analyze just first order dynamical system with this periodicity property. You do that, you get certain results depending on the two parameters that I have. And now question is that all this, what does it have? Does it have any meaning? What kind of a physical system am I talking about? Alright, so let's take one example. So the simplest pendulum, which is not restricted to be small angle. So fixed length, not small angle, so capable of large angle oscillation. This angle is theta. I want to write down the equation of motion. So you take the torque of this and the rate of change of angular momentum equal to the torque. So m times L square theta double dot. So angular momentum ml square theta dot, theta, and the rate of change of angular momentum is that, and that's equal to your torque, which you are going to have. The torque is provided by gravity, which is this mg over here. Tension has no torque, so it's equal to minus mgl sine theta. So theta double dot plus g over L sine theta is equal to 0. So this pendulum has a equation of motion. This pendulum with arbitrary amplitude has an equation of motion which is theta double dot plus g over L sine theta equal to 0. So this is undamped motion of the pendulum. Now suppose I take into account the viscosity of the medium in which it is oscillating, then there would be a Stokes drag on it, which is proportional to viscosity and the velocity. So there would be a term which is like theta double dot plus, let's say, 2k theta dot, that's the viscous drag, k is proportional to the viscosity, plus omega square sine theta equal to 0. So this is include damping. So include damping. Now you have this, and finally you say that, aha, let me put a torque, have an external torque gamma about the suspension point, and if I have this torque gamma, then I would have ml square theta double dot plus this damping term over here, 2k, let's say ml square theta dot, which is equal to the gravity torque, which is minus mgl sine theta, plus an external constant torque that you have applied, which is gamma. And so this equation of motion is theta double dot plus 2k theta dot plus omega square sine theta equals gamma over ml square equal to some constant, it's omega square. So now theta double dot plus, but there is this theta double dot over here, so which is very different from what I have been talking about, which is theta dot. So if you go to high damping limit, high damping, which means that 2k, now what is high damping? There is a time scale involved in this problem over here. So if I look at the dimensions of this, these terms, this term has the dimension 1 over t squared. So d theta dt squared, so the dimension is this. This term has a dimension which is 2k over t. So this 2k over t has got to be much larger than 1 over t square. So this 2k over t, so 2k has to be much greater than 1 over t, which is roughly the frequency, the basic frequency of the problem, which is omega. So you want this damping 2k to be much greater than the natural frequency of the problem omega, in order that you can drop this term over here and reduce the dynamics to the kind that we have been talking about. So very high damping limit, but now if the point is that if you would like to have this kind of a high damping, you would have to imagine that you have this pitch blend in one of these vats, and you are oscillating a pendulum bob inside that pitch blend. Not really a very practical business, right? You want this damping to be so big. The damping is bigger than the natural frequency of oscillation. So this damping has to be huge. And so this example is, all right. It does give you in terms of a pendulum, a realization of what we have been talking about, but at a cost that this realization is for the pendulum moving in a medium which is, just unimaginably viscous. So you want a somewhat better physical system which would be still, which would make better sense, that parameters would work out better for it. So what is the next thing that you can think about, which can be made a more realistic physical system for this kind of case. So that is what is called a Josephson junction. So the next thing I want to do is talk about a Josephson junction in reasonably heuristic terms. So the first thing I need to have is something called a superconductor. So this superconductor is something which can essentially carry at t equal to 0 a current. If you are at very, very low temperatures, very close to absolute 0, it would be able to carry a current without any effective dissipation. The way it manages to do that is to you have these in a metal, you have the electrons, picture the metal as this electron gas with the region up to the Fermi level occupied. So all states up to the Fermi level are occupied. And now the interesting point is that in some metals where the coupling between the electrons and lattice vibrations is large, funny things can happen at near the Fermi levels. Why is that? I mean, it's effectively like this. That imagine I have this lattice over here. The lattice is defined by the fact that there are atoms sitting at these positions, and there are electrons moving through. So these are essentially these positively charged centers sitting over here, and then there is this free electron gas moving around. Now, suppose this electron which comes close to this lattice point over here, there is going to be this Coulomb interaction. So the electron over here, one electron comes round and interacts with this lattice over here through the Coulomb attraction, and while this certainly pulls the electron into whatever its trajectory should be, there is also the effect, although very small, of the lattice being distorted because of the effect of the electron. So the electron, while the positive charge center makes the electron go along in its trajectory in some fashion, whatever the trajectory comes out of a calculation, the electron also, by the equal and opposite interaction, has the ability to distort the lattice a little bit. Comes another electron, let's say, behind it. And now it sees this one has moved away and distorted the lattice a little bit and comes over here. And this electron now is going to see a distorted lattice, and had the lattice not distorted, so this is my undistorted lattice, electron 1 comes and goes off in this trajectory somewhere over here. Electron 2 comes and goes off along some trajectory, let's say, which looks like this, and the trajectories are commensurate with whatever the Coulomb repulsion E square over R12 between the square, if I'm talking about forces, there is going to be the repulsion between these two and the attraction with this over here, that eventually will decide what kind of trajectories you have. And suppose this were static, did not react at all to this first electron, then you would see something like this. But now comes this question of this one after the first chap has moved off in this trajectory. This chap has moved from here to, let's say, in a very exaggerated picture, somewhere over here. And now the second one will not follow this trajectory, but will follow a different trajectory. So this second chap follows a different trajectory, and now when you look at the different, you say, aha, effectively the interaction between these two electrons, which was, I mean, this E square over R12 square, that has, you can view it, the effect of the movement of this lattice as changing the interaction between electron 1, effectively changing the interaction between electron 1 and electron 2. This is how a lattice mediates interaction between two electrons, and this lattice mediated interaction between two electrons are capable of inducing an instability of these electrons near the Fermi surface. What it does, what this effect does, is to bring in effective attraction between the electrons. All this is normally, I mean, if I'm talking about a couple of electrons over here, nothing really is going to happen. But when it is near the Fermi surface, then this effect is enhanced, and you can see effective attraction between the two electrons near the Fermi surface, and this Fermi surface gets destabilized. The electrons form, there is a bound state possible with electron 1 and electron 2 can form at the Fermi surface a very loosely bound state. So this electron 1 and electron 2, they have when the interaction is the maximum, they have equal and opposite momentum, they have equal and opposite spin. So it's equal and opposite momentum, equal and opposite spin. So this pair over here is like a spin zero system and behaves like a boson. And just as bosons give you superfluidity and frictionless flow, the electrons, these which form the pairs called Cooper pairs, these Cooper pairs over here, they condense, and you have the at very low temperatures, and you have the possibility of a flow without dissipation, which is the resistance. So this is what a superconductor, this is how superconductivity happens in traditional materials, where electron-phonon coupling, that is the coupling of the electron with the lattice, is the dominant mechanism. Very good. All right. So now I have this. Now what characterizes the superconductor then are these the bosonic pairs, the Cooper pairs over here, and one can talk about, this is the, take me for granted, you can talk about, discuss things effectively in terms of single particle wave function. This is because essentially what has happened is that you have this the bosonic wave function of the Cooper pairs, and so if I have n of them, I can just write down a string of, for the ground state, a string of wave functions for each pair, just multiply them, and therefore effectively I can think of only one wave function of a single pair. So it's like a single particle wave function happens also in the description of this Bose-Einstein condensates, where things are much more easy because it's a boson to begin with. Here the electrons have formed a pair and effectively a boson, and it is this pair, wave function of this pair, which you are thinking of as a single particle wave function, and you have n pairs which are essentially independent of each other, so the wave function is a string, just a multiplicative string of wave functions. No question of antisymmetrizing and things like that, and therefore a single particle picture does things for you. So there is a single particle description at the end of the day. For this superconducting, the superconductor that we have. So a superconductor at very low temperatures producing this dissipation less current flow because of the condensation of these pairs into a ground state. Now, so all right, now what are we after? We are after a situation where I have a superconductor 1 and I have a very thin gap. So you have S1 and S2, two superconductors separated by a very thin gap.
Sir.
Yep.
Sir, when the second electron comes, we are thinking of it as a pair. But then considering that these pairs are independent. And why that so? Because the second electron also distorts it. The third electron, when it comes, it feels that distorted.
Yeah, I mean, all right. The system is dilute enough that, I mean, the three particle effects are not relevant. So, I mean, it is just two of them, interaction between two. It is not, I mean, the third where it comes, I mean, it's not the effect of three of them doing something, forming, all right, let's say the issue is three of them forming about two is already a very loosely bound state. The probability of three of them forming a bound state is virtually zero. So that's that's why. So for the two particle bound state is already tremendously loosely bound. I mean, the effects are very small. I mean, all these interaction effects that are taking place, they are happening very near the Fermi surface, and then they are extremely small, so small that it is actually exponentially small. So, you have this two superconductors, and with a very thin gap in between, and what Josephson found was that there could be a tunneling supercurrent from S1 to S2. So the wave function of this which I talked about, that wave function, it leaks out. I mean, all wave functions have this property that they exponentially die out at infinity. So the wave functions over here has a tail which gets into this region, and because there is a question of this wave function, if this one is close enough to this, then the tail is still prominent enough to make a current flow across this junction over here. So that is the Josephson effect, the flow of the supercurrent from superconductor 1 to 2 across a very thin gap. So what we want to do is try and find out what kind of current voltage relationships can we expect. That's the thing that I want to do next. So we are going to talk about So this system over here is described by some wave function psi, the S1 and S2 described in terms of some wave function psi, which is going to be superposition of a wave function appropriate to S1 and a state appropriate to S2. So you have this question of, that is, you are allowing for, imagine I am allowing for tunneling. So imagine that I have all the pairs on this side over here and the tunnel, and you have another situation with all the pairs on this side over here. So I have two idealized situations where pairs exist over here, no pairs over here, and then pairs exist over here and no pairs over here. So two states, one which is the superconducting state of this one, and two which is the superconducting state of this one, and in general this will be the state of the state of S1 and S2 will be psi 1 1 plus psi 2 2, where psi 1 2 are complex numbers with psi 1 mod squared plus psi 2 mod squared equal to 1. So you describe in the crudest picture possible this Josephson junction as a two-state system, all bosons in S1 or all bosons in S2, the bosons being the Cooper pairs, and the one which is appropriate to S1, two which is appropriate to S2, and the general state of the system being of this kind. So alright, this is it's a two-state system quantum mechanics, and the two states are 1 and 2, and with amplitude psi 1 and psi 2, they give you the wave function of the system. So now what's the wave, there is some Hamiltonian, the dynamics is going to be IH del psi del t equal to H psi, where H is the relevant Hamiltonian of the two-state system. So alright, now how does one handle this dynamics over here? This is, the time dependence are in these coefficients psi 1 and psi 2. So let me write out IH del psi 1 del t 1 plus IH del psi 2 del t 2, that's equal to H psi 1 1 plus psi 2 H 2. If you take a inner product with the state 1, then IH del psi 1 del t is equal to psi 1 1 H 1 plus psi 2 in 1 H 2, and similarly with IH del psi 2 del t is psi 2 H 2 plus psi 1. So that's the pure two-state system dynamics. We are not saying anything new at all. Well, I mean, this is exactly what you will find in the relevant part of Feynman Volume 3. So now I have to talk about the matrix elements. So the matrix elements 1H2 and 2H1 describe the possibility of hopping from 1 to 2. So hopping from 1 to 2, these matrix elements 1H2 you write equal to 2H1 equal to what is conventionally written as minus W. So that's the hopping possibility. So that is the electron, the wave function can tunnel from here to here. One H1 is the energy. If I didn't have any connection whatsoever, then it is no hopping or nothing at all. Then 1H1 would just be the ground state energy of system 1, and so it's a property of 1. And if I, for what I'm going to describe, the flow of a charge from here, these flow of these super pair, for these Cooper pairs from here to here, there would be some kind of a voltage difference which would be driving it. So the energy over here, which is, let's say, E1, one writes as in terms of a voltage, so charge times voltage, that would be the energy. The charge is minus 2E for every Cooper pair, so it is minus 2E times V1, where V1 is the voltage associated with S1, and 2H2 is equal to minus 2E V2, where this is the voltage difference V1 minus V2, which would be responsible for driving the current across the junction.
So these are external voltage or these V1, V2 are
V1, V2 are internal properties, right?
internal properties.
I mean that's the ground state energy difference which I'm writing at. So you connect it to some. So I get at the end of the day then IH del psi 1 del T is minus 2 EV1 psi 1 minus W psi 2 IH bar del psi 2 del T is minus W psi 1 minus 2 EV2 psi 2. Good. So nothing which is very esoteric, and the next step comes now, that once again the question, I mean till now we had just said that I have this S1, a superconductor over here, which would be generally described by the state 1, this by the state 2, and these two taken together. 1 and 2 are the basic states of the basis states of the system, and you have this linear combination. Write down Schrödinger equation and just definitions, and you have come over here. Now comes the next question, that all right. Suppose I have to, this psi 1 and psi 2 are complex numbers. So let's say I have put n1 particles, that is n1 pairs in 1, S1, and n2 pairs in S2. N1 plus N2 is n, let's say, the total number of pairs, and N1 is equal to psi 1 mod square. So what is the meaning in terms of these number of pairs? What's the meaning of these numbers, psi 1, psi 2, complex numbers that I have introduced over here? N1 plus N2 is total N, so N1 is psi 1 mod square N, N2 is psi 2 mod square N. So if N is the total number, the probability P1 over here tells you of what's the probability of its being on the side 1, what's the probability of its being on the side 2. So number of particles on side 1 and side 2 related to n by the probability factors psi 1 mod square and psi 2 mod square, which one will call psi 1 mod square equal to some small n1 and psi 2 mod square equal to some small n2. Psi 1 is a complex number, so which I'll now write as psi 1 equal to square root of n1 e to the power minus I theta 1, and psi 2 is equal to square root of n2 e to the power theta 2. We come back and put this over here. So psi 1, that transformation is IH, and then it is del t of square root of n1 e to the power minus I theta 1 minus I del theta 1 del t, and there is e to the power minus I theta 1 sitting outside, which is minus 2 EV times square root of n1. This also has an e to the power minus I theta 1 minus w and e to the power I theta 1 minus theta 2. So I've taken the minus theta 1 from here, put it on this side, the phase has cancelled over here, and I have the phase difference over here.
In the left hand side, the del theta 1 del t will contain a root over n1. And in the right hand
There
side,
should have been an n1 here, na?
root over
Yes,
n1.
root n.
Root over n, root n1.
And the right
Yeah.
side, w
Root n2. Yeah. Thank you. Yeah. So real and imaginary parts. Equate real and imaginary parts. Then h bar square root of n1 del theta 1 del t is equal to minus 2 EV square root of n1 minus w square root of n2 cosine of theta 1 minus theta 2. Real part is IH over 2 square root of n1 del n1 del t, that is imaginary part, h bar over 2 square root of n1 del n1 del t is equal to, there is a minus here, minus w square root of n2 sine of theta 1 minus theta 2. Same things with h bar n2 del theta 2 del t is minus 2e, this should have been v1, minus 2e v2 square root of n2 minus w square root of n1 cosine theta 2 minus theta 1, which is the same as theta 1 minus theta 2, and h bar of 2 root square root of n2 dn2 dt is equal to minus w square root of n1. Now that's a plus, as theta 2 and theta 1 gets changed, so sine of theta 1 minus theta 2. So alright, from these two over here, we find that, alright, take this slowly, we are almost done. Let me just do it a little carefully. N1 particles here and N2 particles there. Now you note that from here, as expected, del T, so H bar over 2 del N1 del T is equal to minus W square root of N1 N2 sine of theta 1 minus theta 2, and H bar by 2 del N2 del T equal to W square root of N1 N2 sine of theta 1 minus theta 2. So del T of N1 plus N2 is equal to 0, as it should be, because N1 plus N2 is equal to 1. So N1 sine 1 mod square plus sine, that was the normalization of it. And so you want del T, whatever dynamics you do, del T of N1 plus N2 should be 0, which is exactly what has happened. So the total number is there. Now what's the current? The particle current, so going from 1 to 2, it's N1, let's say tunneling from here to here. So the rate of N1 going down. So particle current is minus dN1 dt. Each particle carries minus 2e, so electric current is 2e dN1 dt. So you look at this, N1 so the first small n1 is capital N1 divided by total n, which is a constant. So this is h bar by 2 del dN1 dt divided by capital N. So divided by capital N is equal to minus W square root of N1 N2 sine whatever that part, and it is this current. Therefore the current I is equal to 2E times, so 2E into del N1 del T, so it is N into 2W divided by H bar, and it is square root of N1 N2 sine of this phase difference with a minus sign. Yeah? So minus 2 En 2W over H bar square root of this phase difference theta 1. So let me call the phase difference theta 1 minus theta 2 as theta. So I is equal to minus this, and alright, so that's up to now with no approximations at all. Now you assume that the current is small, tunneling current is small, so changes in N1 and N2 are small. So to the first order, N1 and N2, small N1 and N2, so this difference N1 minus is small, N1 very nearly equal to N2 equal to N over 2, so that this square root over here, so this N1, N squared, so that becomes N divided by 2, gets rid of one of the 2's over here, which is minus 2 EW H bar N squared sine theta. So that's I, the current across the junction in terms of the phase difference, and this is generally written as I equal to IC, that's the maximum value of the current times sine theta, which is the first or one of the two Josephson relations for the current, I equal to IC sine theta. There is another relation which now has to come from here. Over here you note that if I take the difference, so this root N1 is going to disappear from here, and I have square root of N1 over here. This N2 disappears from here, and I have a square root of N2. And in the approximation that N1 and N2 are very nearly equal to each other, then therefore this is, if I subtract these two, this is going to cancel out, and you are going to have H bar del theta del t, the rate of change of phase, is equal to minus 2E times the voltage difference V1 minus V2. So the voltage difference across this junction and the two superconductors S1 and S2, which is essentially the chemical potential of the junction, that drives the phase of it. The phase, the time derivative of the phase is the energy difference, which is V1 minus V2. Energy differences are like the chemical potential, so it is the chemical potential which is like theta dot. So that's the phase equation, and over here what is the current across the junction? The current across the junction is determined by the phase over here. So the phase determines the current, the dynamics of the phase is determined by the chemical potential, which is essentially the voltage difference. So that is Josephson, those are the two Josephson junction relations which one writes down for very small current, small changes in the number of particles N1 and N2, and you have this relation over, these relations over here. Now what, alright, so there is this where we are beginning to see the ingredients coming in. There is a phase relationship, dynamics of the phase being connected to a voltage difference. There is a phase determining also the current. Phase determines current. The dynamics of the phase determines the voltage difference. And now let's say I want to put all this knowledge together. So what are we going to do? We do the following. One looks at what is called a biased junction. What a biased junction is, biased in the sense that a constant current I flows across the junction. So that's what a current bias junction with a current bias is. So there is a constant current I which flows across the junction. Now what happens, what does I consist of? you have this supercurrent, which we have just derived. So in terms of the system parameters, I have a supercurrent which is IC times sine theta, and then if it is not t equal to 0, when at t equal to 0 it's all supercurrent, but then there are normal unpaired electrons which will give you current at t not equal to 0, which is generally always the case. It's not t equal to 0, so there would be some I normal current, which would simply be V over R. If there is a shunt resistance R in the circuit, then that would be voltage difference divided by R, plus there could be some displacement current. Why? Because there is this capacitor formed over there between these two superconductors, and you would have Q equal to C, the capacitance of the junction, times the voltage difference, really, delta V. So Q equal to C times V, and there would be a current which is I equal to the minus dq dt, simply because taking into account the fact Q is negative. So it's negative charges flowing, so I would be equal to minus dq dt. So there would be a displacement current, so this is I displacement. So there is a I displacement that you are going to get over here. So these are your currents that you have going. You will have a supercurrent, you will have a normal current, you will have a displacement current, and so there would be a circuit which looks like this. So I would have a circuit which, here is a current source giving me constant current, and this constant current is divided into this supercurrent over here, divides into the supercurrent, divides into the resistive current and the capacitor current that you get from over here. So the total current I coming out of this bias, the current biasing, is I supercurrent plus I displacement current plus I normal current. And now we are through. Give or take signs which I might get wrong and be a little embarrassing at the end of the day, but if that happens, I'll just request you to correct the, well, whatever happened, really the embarrassing thing could be the minus sign becoming plus sign. These things go. So, alright, so I is equal to I supercurrent, IC times sine theta, all sine's height in IC, so nothing can go wrong at that point. So then you have the normal current. Normal current is V over R. Getting to be tricky now. V is this delta V over here, and I have minus, so it's this delta V, which is this minus h bar over 2 epsilon theta dot. So you have your theta dot, and then the displacement current, which is minus dq dt, which is minus c minus C, C is the capacitance which doesn't change, times dV/dt. Now the time of reckoning.
Sir,
So,
will there be resistance R?
huh?
That equate between R. R due to resistance. That
Which one should
delta V by R. That
Normal.
This should be resistance 1 over R.
1 over R. Thank you. So dV/dt, Josephson junction, is this one over here. So dV/dt is supposed to be minus h bar over 2 epsilon theta double dot. Yeah. So I see IC was this negative term minus 2EW. So I have so there goes my problem. Okay, all right, we'll have to see where one gets off. There's going to be a sign, but I see looking at from there is minus. I have a problem with the IC. This is dq dt, I displacement minus, I displacement is minus C dV dt, it's negative charges, and it's IC, something wrong with my IC. I've missed some factor in IC. What happened? What happened? It was minus dN1 dt. No, lost. It was minus dN. Say. Suddenly, I mean, I'm missing, I mean, it should have been 4e squared. I mean, a factor of 2e is certainly missing. I think also a factor of h bar is missing in the denominator. I have a problem with the expression for IC. So it should have been RE supercurrent, that was this minus dN1 dt, that is the rate at which I am losing particles N1. N1, the particles of charge 2e, so it is dN1 dt, it is 2e n, and it is dN1, here, dN1 dt, dN1 dt, and dN1 dt dN1 dt should have okay, I see. So this is equal to 2En, and dN1 dt, do I have it? That's the one over there, which is minus W. So it is dN1 dt, which is N is N1, this is N dt, which is what I have written up over there. dn1 dt is minus w square root of is n times square root of n1 n2 and is 2 over h bar, right? Sine theta. Okay. So sine theta, that is I equal to minus dl is 2d minus 2ew minus 2ew and this, so that's 4, that's n1 by n by 2, n by 2, so it's n squared. So I is this, I seems to be right, it is minus 2 over h bar w n squared sine theta. That's my I. So if this is IC sine theta, and then if I didn't have anything else, then it would just be Q equal to CV. Q equal to CV is the charge over there. So there is going to be a current. This is going to be this is going to be the current over here. The current over here must balance that current over there if I don't have a biasing. So Q equal to CV, I displacement, this is negative charge over here. So I should have for I displacement a minus dq dt. So that is minus C. So this is minus C dv dt, minus C dv dt, and dv dt is my, so this becomes a plus, and it is C times h bar over 2e times d theta dt. So it is this current I displacement should be the entire, should be balanced by the supercurrent, and so the sum of the two should be equal to 0. Now this is where am I biasing myself with that Q equal to CV, putting in the negative sign as a that probably this is Q equal to CV. That this is sorry. That's my the bias. That I can't have a bias with Q equal to CV. That's the I write down whatever the displacement current is. So I can't have a bias here. That's my problem. Alright, so I displacement is simply, dq dt, and displacement current is this, which is C dv dt, which is equal to the current over here, which is h bar. So it is minus C h bar over 2e theta double dot. So that's the displacement current, which has to balance out this current over here. So no biasing. So displacement current plus the supercurrent has to give me 0. So it is minus CH bar over 2e theta double dot minus 2e over h bar. Alright, got the factor. N squared sine theta. That has to be equal to 0 if I have no bias, and no question of a regular current. So no question of a normal current, whether this is just the supercurrent being balanced out by the displacement current that would come from that circuit. But if you have a bias and you have a resistive current over here, then it is I equal to IC sine theta minus this quantity over here plus this C times dV dt over here. IC sine theta is equal to minus 2E over h bar W n square sine theta. That's IC sine theta minus h bar over 2ER theta dot plus CV, which is minus C times h bar over 2E times theta double dot. Alright, so that's the biasing current, and so C times theta double dot plus theta dot divided by R plus 4E square over h bar square W times n square sine theta equal to minus I, the bias current. That's the equation. So Josephson junction under a biasing current I, the equation of motion is C theta double dot plus this plus sine theta equal to minus I. Now C is the capacitance of the junction, and now once again let's look at the time scales. The time scales, the frequency of motion, the frequency omega square, that's the coefficient of sine theta, theta double dot plus omega square sine theta. So theta, this is 4E square W into n square over h bar square divided by C. That's the frequency of the oscillation in this circuit. If this is absent and theta is small, that's the frequency of oscillation, which is omega square given by that. And theta double dot, so now I'm looking at the question of is this term big or this term big. Then I'm looking at C times omega square, which I will compare with 1 over R times omega. So it is C times R to be compared with this 1 over omega. So C times R with 1 over omega coming from there. So omega equals 2E n square root of W h bar square root of C. So it is CR to be compared with 1 over omega. So CR to be compared with h bar square root of C divided by 2En square root of omega. And you want the CR to be much smaller. So that's then this quantity over here. So it is square root of C. You want it much smaller than h bar over 2E nr square root of W. So that's the condition that you want in order that this may be droppable. And now if you look at the right hand side over here, you have a extremely small term over here, but then you have a resistance which is also going to be extremely small, and a tunneling probability which is extremely small, E which is extremely small, and N which is large. So there are terms which in the denominator can become extremely small, a term in the numerator which is extremely small, and it is actually possible for this quantity, the the dimensionless parameter over here, that is this multiplied by h bar, to range over several decades. So from 10 to the power minus something to 10 to the power plus something. So here in the Josephson junction, you have a situation where this can actually be dropped, and there would be system parameters for which your equation of motion is indeed the theta dot equal to f of theta that we started out with. So if there is any place where what we have discussed today about the fixed points and the merging of fixed points and then the periodic orbit and so on, then it is actually the resistively shunted biased Josephson junction, which forms a very practical way, a very practical testing ground of the dynamics of the kind we have discussed. So this is, I mean, to sort of, you will find the things written down, and this parameter discussed in Strogatz under the name of Macomber parameter, but it is for once nice to see where all this comes from. That's why it's worth the digression, and point out that the Josephson equations with some picture of the superconducting state can emerge from two-state quantum mechanics. Nothing new, as I said, Feynman volume 3 has it all, but all right, I mean, good to see. So that's what this was all about, to get the form which we talked about, and to get it to actually show an equation of motion where the kind of approximations that we made to get at theta dot equal to f of theta is not really unrealistic. In real life, you can actually see transitions from behavior dominated by this to behavior where this term over here begins to play an important role. And the difference, as you can imagine very clearly, is that in theta dot equal to f of theta, when we have talked about a periodic state, there was no fixed point. And when we introduced fixed points, there was no periodic state. This total dynamics over here has a fixed point. Theta dot and theta double dot both equal to 0 would give a fixed point corresponding to sine theta c equal to minus I divided. So there is a fixed point. And also, being a second order differential equation, just imagine small theta over here, there is a periodic solution. So over here, you would actually see a periodic solution simultaneously coexisting with a fixed point, colliding, and interesting things happen. That's why later on we would again have occasion to come back to this when we do second order systems. But for the time being, this second order system can be, under very normal circumstances, even a good approximation to a first order system. So that's it. That I still have, to finish this off, I want to discuss the question of synchronization in these phase variables. So the last lecture on anyone would be on synchronization. I told you before that I'd be away, but I could do some changes. So Wednesday, 27th, I will be here in the morning. So we will have the 9:30 class on Wednesday. Thursday I won't be here, and we'll make up on Saturday at 11. So, but for the time being, 9:30, Wednesday, 27th, we are on. And for those of you who are still, I mean, I do want a class list for mailing and so on, and also for setting up a forum where people can talk about class material, ask clarification, and so on and so forth. There is a pretty neat forum called piazza courses, and one can actually, but for that one needs to know who are the students in the class, and we can set up the discussion forum on that.
বেজে গেছে।